At 1:23 a.m. on April 26, 1986, residents of Pripyat living near the Chernobyl nuclear power plant heard a loud explosion. They did not know that they were about to witness the worst nuclear accident in history, one that would change their lives and the lives of millions of others forever. The Chernobyl nuclear power plant was located in the north of the Ukrainian SSR, near the city of Pripyat. It consisted of four reactors, each capable of producing 1000 megawatts of electric power. The plant was built in the 1970s and came online in the 1977. It was considered a model of Soviet engineering and a source of pride for the communist regime. Chernobyl's nuclear reactor was a type of reactor known as the RBMK 1000. The RBMK 1000 was a graphite moderated water cooled reactor designed by the Soviet Union. The reactor at the Chernobyl nuclear power plant had several key components and operated based on the principle of nuclear fission. Nuclear fission is a nuclear reaction in which the nucleus of an atom is split into two or more smaller nuclei. This process releases a large amount of energy. The nucleus of an atom is made up of neutrons and protons. When a heavy nucleus such as uranium 235 absorbs a neutron, it becomes unstable and can undergo fission and start a chain reaction. To understand what went wrong, we first need to know how a nuclear reactor works. The RBMK 1000 used uranium 235 as fuel. Uranium fuel was loaded into fuel assemblies. These fuel assemblies were then inserted into vertical channels in the reactor core. Graphite blocks were used as the moderator in the RBMK 1000 reactor. The moderator slows down the fast moving neutrons released during the fission process, making them more likely to cause additional fission reactions, increasing the reactivity. The graphite blocks surrounded the fuel channels, providing moderation. The reactor had control rods made of a neutron absorbing material, boron. These control rods were inserted or withdrawn to control the rate of the nuclear reaction by absorbing excess neutrons and thus reducing the reactivity of the core. In normal operation, only a few control rods were inserted to maintain the desired power level. Water served as both a coolant and a neutron moderator. It circulated through a series of horizontal pipes known as the reactor's primary cooling circuit surrounding the fuel channels. The water absorbed the heat generated by the fuel and carried it away, preventing overheating. Heat from the reactor core was transferred to a secondary cooling circuit through heat exchangers. In the secondary circuit, water was converted into steam. This steam was used to drive turbines, generating electricity in the plant's turbine hall. On the night of the disaster, the plant operators were conducting a safety test on reactor number 4. The test was intended to simulate a hypothetical scenario where the reactor lost power and the emergency backup systems were unavailable. The goal was to evaluate whether the residual rotational energy from the steam turbine could provide enough power to operate the reactor's emergency systems until the diesel generators kicked in. These emergency systems were essential for cooling the reactor and preventing a potential meltdown. To conduct the test, the operators needed to reduce the reactor's power to a low value. However, due to the inherent design flaws of the RBMK 1000, specifically its positive void coefficient, the reactor became highly unstable at low power levels. This flaw caused a significant increase in reactivity when steam voids formed in the coolant, leading to a positive feedback loop. Something to note here is that the operators assigned to oversee the test were not adequately prepared or even qualified to handle the complexities and risks associated with the experiment. During the test, the operators began reducing the reactor's power level by inserting control rods into the core. However, a combination of design flaws and operator errors led to a sudden and uncontrolled power surge, resulting in a rapid increase in reactor power. In a desperate attempt to mitigate the escalating situation, the operators pressed the AZ5 button. The AZ5 button was a large red button located in the control room of the Chernobyl RBMK-1000 reactor. Its purpose was to initiate an emergency shutdown of the reactor in the event of an unforeseen or dangerous situation. Pressing the AZ5 button would trigger a rapid insertion of all the control rods into the reactor core, aiming to halt the nuclear chain reaction and bring the reactor to a safe state. Tragically, the design flaw known as the positive void coefficient, where the reactor's reactivity increased under certain conditions, worked against them. The sudden insertion of the control rods instead of immediately halting the reaction caused an additional increase in power. The power surge caused a destructive steam explosion and subsequent graphite fire, leading to a massive release of radioactive materials into the environment. But why? Shouldn't the rods have absorbed the neutrons and stopped the nuclear reaction? It should have, but the inserted control rods were in two halves, and the first half was graphite. So when the AZ5 button was pressed, the graphite entered the core first, which initially displaced water coolant and introduced additional reactivity to the core. This, combined with the high power levels and other contributing factors, led to a destructive steam explosion and subsequent graphite fire. The reactor's containment structure was also severely damaged, and a large amount of radioactive material was released into the environment. The explosions also blew off the heavy steel and concrete lid of the reactor, exposing the burning core to the air. The lid was estimated to weigh around 2,000 metric tons. The fire that ensued lasted for 10 days and released about as much radiation as the initial explosions. The radioactive plume spread over large parts of Europe, contaminating soil, water, plants, animals, and humans. The Soviet authorities initially tried to cover up the accident and downplay its consequences, but they soon had to admit the truth and ask for international help. The immediate response to the disaster involved more than 500,000 personnel and cost an estimated 18 billion rubles, about 68 billion US dollars. The workers who entered the plant to fight the fire, seal off the reactor, and clean up the debris were exposed to lethal doses of radiation, and many of them died or suffered from severe health problems. A 10-kilometer radius exclusion zone was created around the plant, from which about 49,000 people were evacuated, mainly from Pripyat. The long-term effects of the disaster are still being studied and debated. According to various estimates, between 4,000 and 93,000 people died as a result of radiation exposure or related diseases. Millions more were affected by increased risk of cancer, birth defect, psychological disorders, and social problems. The environmental impact was also significant as large areas of land became uninhabitable or unsafe for agriculture and wildlife and will remain highly radioactive for thousands of years.